Hello everyone, welcome to class. Today we will introduce recurrent neural networks, RNN, and the long short-term memory, LSTM. RNN and the LSTM can be used to process time series data. A time series data is a series of data tracked over time. Some examples include temperature, speech, or stock price. Those data are time series data. Recurrent neural networks can solve a problem of feed-forward networks. The feed-forward networks, such as densely connected networks or convolutional neural networks, don't consider the temporal states. In other words, feed-forward networks don't consider the relationship between current sample and the previous samples. For some kind of data, especially time series data, the relationship between current and previous samples is very important. Here's an example of time series data. This is the historical price of Nasdaq. So we need to use the previous price to predict next price. To solve this problem, RNN proposed to use a loop to memorize the previous information. Okay, here's the picture of RNN. So RNN has a loop recurrent connection, which resend the output back to itself. And the RNN has a memory to remember the previous output. And when a next input comes in, RNN will calculate a new output based on current input and the previous output. So recurrent neural networks can remember or can memorize previous data and the previous state. Therefore, consider the temporal relationship. To better understand how it works, we can unroll the RNN loop in the time domain. Let's look at this picture. This is one neuron, one RNN neuron. And the input is a time series data X, and output is a time series data H. So first, we unroll the data, input data in the time domain. So let's show the data from the beginning, x0, x1, x2 to xt. And then we will have the output h0, h1, h2. So now we can better see that the RNN cell, remember we only have one cell, but this is the same cell at a different time. So RNN will consider the previous input x0 and save the state, the output state, then pass to the next state. So when you have next data x1, then you can use x1 and the previous output to calculate new output h1, and then save the state and then pass the state to next cell. So this picture, the unroll of RNN loop, can better illustrate how RNN works. RNN is effective for speech recognition, language modeling, and language translation. It's very good for process time series data. Let's implement a simple RNN using pseudocode. Here is an example. First, we need a memory to save the previous state. We name the variable state t. Okay, so for each input from the input sequence, because it's a time series data, we will pass the input t and the state t into a function, activation function, and then we can calculate output t. The key point is to save the output t to state t to make a loop, right? To save the current output to the state and pass to next step. So this is the first version of Pseudo RNN. Okay, the more formal version of Pseudo RNN is here. Now we replace the function f with the more formal activation function like this one. So for the input x, xt, and the previous output yt-1, which is our state, each one has a weight matrix. So the weight matrix W is for the input xt, and the matrix U is for the previous output yt-1 plus a bias. Then we can pass through an activation function and calculate the new output. Okay, so here is the second version of our Pseudo RNN. Okay, for the input sequence, for each input t, for each input at time t, we calculate the dot product of the weight matrix and the input t, and the dot product of matrix U and the state t plus a bias, then goes pass to an activation function to calculate the new output t. Okay, so make a loop to make a loop, we update output t with the state t, and that's our new RNN. Now we are ready to implement our simple RNN using Numpy. Then this code can be used directly to train models. In fact, this is part of the code of simple RNN layer in Keras. So first, we need to define the time steps, how many samples we want to use in a time series data. Here it is 100, and the dimension of input features, which is 32, and the dimension of output features, which is 64. Then we randomly initialize the parameters in the input date tensor and the weight matrix. We use W for the weight matrix of input features, and the U for the weight matrix for the previous output. So the dimension of the weight matrix W is output dimension by input dimension. For the update matrix, for the U matrix is output dimension by output dimension. And finally, we have a bias. Then we have a list to set the output. We will have a series output from our RNN model, so we keep the temporary results. Then we iterate through our input time series data. For each data, we calculate the new output. Here we use tangent h as our activation function. Then we calculate the dot product of the weight matrix with the input and the update matrix with the state t. The state saves the previous output plus a bias. Then we can calculate the new output t. We save the output in our output list, output array, and then we update our memory, our state variable, to update our state variable with new output. So this is our loop. Then we continue iterate through all the input data. Finally, we will have a output array, output list, successive outputs. This is our final output sequence. We can also unroll our simple RNN in a time domain to understand it better. Here, this is our simple cell. Remember, we only have one neuron. Okay, the neuron accepts the input t and the output from previous state. We call it state t, and they use input t and the state t to calculate a new output t. So we have two weight matrix W for input t and the U for state t, and one bias. Then we calculate the new output T and save in the state. We update the output T, save in the state T, and then pass to next stage. Now it's state T plus 1. Okay, then we use state T plus 1 and input T plus 1 to calculate the new output T plus 1. The simple recurrent neural network we have implemented is actually exist in Keras. The layer is just called simple RNN. So let's see how to use simple RNN in Keras. First, we create a sequential model. Then we can add one embedding layer if we want to do natural language processing. Then we can add the simple RNN layer. We can add more than one simple RNN layer. We can stack multiple layers. But if we want to stack multiple layers, the hidden layer, we should set the parameter return sequence to true for the hidden layers. Okay. But for the final layer, we don't need to set recurrent sequence. The return sequence will return all the sequential output, right? Remember the successive output sequence. Remember all the output sequence to the next layer. But the final layer, we just output the data one by one. So we don't need to set the return sequence to true. Let's see the number of parameters in each layer. For the embedding layers, it's just the input dimension 32 multiplied, the input dimension 10,000 multiplied by the output dimension 32. So it's 320,000. And for each embedding simple RNN, right? Because we have two matrices. Remember, we have the matrix W and the matrix U, each are 32. So it's 32 plus 32, U plus bias. Multiplied by the output is also 32, right? So it's equal to 2080. Although recurrent neural networks usually only have one neuron, it also suffers the managed and exploding gradient problems like deep neural networks. This is because the recurrent neural network need to process time series data, right? If we unroll the RNN in the time domain, the weight matrix, the backpropagation algorithm still need to go back to multiple time series data. It's just like a deep neural networks. So RNN also suffer the managed and exploding gradient problems. To solve the gradient managed and exploding problem, the researcher Schumacher proposed a model called long short-term memory. It was very successful. The long short-term memory add multiple gates. First, they add an input gate to control if we want to let the new input in or ignore the input. And then it add the forget gate, so it can delete the trivial information. It simulates the ability of human that we usually forget some trivial or unhappy things, right? So human can forget trivial information. And then the output gate, it can decide if to let the information impact the output at the current time step or not. So this is the original figure in the paper. Here is the input, and we have an input gate. The gate usually output from 0 to 1. So if the output is 0, then the input will be ignored. If the gate output is 1, then the input will pass through to the hidden cell. So the gate is like a switch, and it can output continuously from 0 to 1, so you can control the part of input that pass to the hidden cell. So another gate is the forget gate. If the forget gate is 0, right? So you will clean the memory, the hidden cell, right, to 0. The last one is output gate, or is control the output. Decide if we want to let the information pass to next stage or not. The original LSTM picture is not easy to understand. Keras has made a new version of LSTM picture. Here is the picture. So from this one, we can see that, or we can think that LSTM model has two paths. One is to update the cell state, the memory in the model. Another one is like the original RNN to pass the output to next stage. So for LSTM, we can think that it has two paths to pass the data to next stage. The first is the cell state. So the forget gate can control if we want to forget information. The sigma means the sigmoid activation function. Remember, the output of sigmoid is between 0 and 1. So we can use sigmoid activation function like a switch. 0 means turn off, and 1 means turn on. And we can also assign value between 0 and 1 to control the portion of the information. So we just multiply the activation output with the previous cell state to generate the new cell state. The second is the input gate. We can control if we want to how much information we want to pass, how much input information we want to pass into the cell state. And the input activation function is tangent H. Okay, the third gate is the output gate. We can control how much information we want to pass to next stage. So from this version of LSTM, we can understand that in fact we can view the LSTM model with two path model. This is the major difference between LSTM and the traditional RNN model. Let's look at the details of LSTM. First, we have a cell state, which saves the state information. And as mentioned before, we have a forget gate, which can control how much information we want to pass to next cell state. How much information of previous cell state CT-1 that we want to pass through. Okay, we use sigmoid function as the control gate. Right? Remember, the output of sigmoid function is between 0 and 1. So 0 means that no pass, right? No information pass to next stage, and the 1 means totally we pass all the information to next stage. Okay. And we can select a value between 0 and 1 to control how much we want to pass. So this is the multiplication. This is how we design a control gate. The first step in LSTM is to decide if to throw away old cell information CT-1. We use a forget gate to control how much information of CT-1 we want to pass to next stage, to the new cell state. Okay. Here's a formula for the forget gate. So we use the input xt and the previous output ht-1. We multiply it by a weight matrix plus a bias to control the activation function sigmoid. So we use the previous output and the new input to decide how much information we want to pass to the new cell or to our cell state. The second step in LSTM is to decide what information we want to store in current cell state CT. Use the previous output and the current input xt. We can calculate a new output CT. So we multiply the new input and the previous output with a matrix WC plus a bias. Then we can calculate a new cell state. Again, we have an input gate that can control how much new cell state information we want to pass and add to previous cell information. So this is how to control the new cell information. The next step is to update the old cell CT-1 with new information. Okay, so it's just the weighted sum of previous cell information and the new cell information. Then we can save the result into our current cell state. Finally, we can use the new cell state to calculate the output. So the new cell state is passed to the tangent edge activation function, and then we can use a control gate to decide how much information we want to pass to next stage. Okay, so once we have a new cell state, we will pass to an activation function, then use the output gate. The output gate is based on the previous output and new input to decide how much information we want to pass to next stage. The LSTM model was so successful that almost everyone chose to use LSTM instead of simple RNN model. There are several variants of LSTM. Because LSTM is complicated, researchers tried to simplify the model. One method is to couple the forget gate with the input gate. Right? So now we can only use one gate to control the forget and update. Right? If we want to update the information, then we forget more about the previous information. But if we want to remember more about the previous information, then we will add less input information, new cell information. So this method coupled the forget gate and the input gate. One of the most popular variant is the gated recurrent unit. It's called GRU. GRU was proposed by Cho in 2014. It combines the forget and input gate into a single update gate, and also it merged the hidden state and the cell state. So it now again only have one path. GRU is much simpler than previous LSTM model, but it has similar performance. So many researchers choose to use GRU. Now let's see how to use LSTM in Keras. We import the LSTM layer from keras.layers, and then we create a sequential model. In this example, we try to use the LSTM to classify text. So we first convert the one-hot encoding text vector into dense embedding vectors. And then we pass the embedding vectors to the LSTM model. Finally, because we want to do classification, we add a sigmoid activation function as the final output. We can train our model using IMS prop and use the binary cross entropy as our loss function. The matrix is accuracy, and we can fit our model to the data. There are several advanced techniques to train RNN models. The first is dropout. We can randomly drop several connections to find overfittings in the recurrent layers. The second is that we can stack in multiple layers of recurrent layers. We have seen this technique before. This can increase the representational power of the network. Remember to set the return sequence parameter to true if you want to stack multiple layers of recurrent networks. And then there is a technique called bidirectional recurrent layers. It can present same information to a recurrent neural network in different ways. It can pass the reverse order of series data into the layers. It may be helpful, may be useful for natural language processing, because sometimes we will say the same sentence in different order, right? So bidirectional may be useful, but it's not good for temporal dependent data. Let's apply recurrent neural networks to predict time series data. The first example is to do temperature forecasting, or to forecast the temperature tomorrow. We use the dataset that measures 14 features every 10 minutes from 2009 to 2016 in Jena, Germany. Okay. Let's visualize our data. Let's draw all the data points. And you can see that the data are quite periodic. That's because there are 4 seasons. So the data changed periodically. But it looks like it's not too difficult to predict the temperature from the global scale, but if we want to try to just predict the temperature in a few days, it will be more challenging, as shown in this picture. We can download the Jena weather dataset from the Amazon Web Service. Here's the link. Before training, remember to normalize the data. Always remember to normalize your data first. So first we calculate the mean of the data set, or it's a continuous data. And then we subtract the mean from the data set. Then we calculate the standard deviation of the data set and then divide the data set by the standard deviation. Next, we have to decide the learning parameters. We need to decide how many data we want to use to predict future data. This is called lookback. In this example, we want to use the previous 5 days to predict the data, to predict the temperature in 24 hours. So 5 days means there are 7,200 minutes in 5 days. Because we measure data every 10 minutes, so we need to look back 720 data samples. So we set the look back period to 720. And then we need to decide the steps. We don't need to use every 10 minutes to predict future temperature. Actually, the temperature won't change a lot in next hour. So we choose the steps to 6, which means we will observe, we will sample data every hour. We will sample at 1 data point per hour. Next is the delay. This is how long we want to predict. This is the target we want to predict. Our target is to predict the temperature in 24 hours. In 1 day. Then we need to design a data generator to subsample time series data from our data set. And then this generator includes the parameters that we want to set. So first, the input is the data, and then we need to set the look back period, which means set how many time steps back the input data should go, and the delay, which means how many data or how many time steps in the future that the target should be. Also, we can set the min and the max index to define the period that we want to draw our data from. This is useful to keep a segment of the data for validation and another for testing. All right, you can define a period that you want to use for training and another period for validation. Also, you can choose if you want to shuffle the samples or not. And then the bench size, right? The bench size we want to draw from the sample space for training each time. Finally, the step, the period in time steps that we want to sample the data. We set it to 6 to sample one data point every hour in our temperature forecasting problem. Here's the code of the generator. First, we check the max index and the min index. Then we loop through the data, all the time series data. If shuffle, then we will randomly shuffle the data. Otherwise, we will draw subsample the data based on the look back period divided by the time step. And then we will subsample the targets. Okay. The rows are the bench size, how many time series we want to extract from this data set. So we will iterate through our data to extract the number of data. We create an index using range and then paste the index to our data to select the samples. And we plus the sample, we plus the output with the delay period and then subsample the targets. We need to create baseline models to compare with our recurrent neural networks. It's only meaningful if our new RNN models are better than baseline models. Otherwise, we can just use the simple baseline models. Okay, the first baseline is called ConvNets. We simply use the temperature as the prediction, which means we simply use the temperature today to predict the temperature tomorrow. And surprisingly, the performance of ConvNets baseline is not bad. It has the mean absolute error 0.29, which is equal to around 2.57 degrees. So if you just use today's temperature in Jena to predict tomorrow's temperature, you will only get around 2.57 difference, which is acceptable for most people, I think. Okay, the second baseline is to use densely connected network to predict temperature. Okay, so we just use one hidden dense layer in the sequential model, and we choose the output dimension to 32. The output is one neuron without activation function because we want to predict continuous data. Okay, so we trained with 20 epochs, and each epoch have 500 steps. Well, here's the result, and again, it's a surprise to see that the densely connected network perform worse than the ConvNets baseline. Okay, and you can see the validation loss is higher than 0.3, and the ConvNets baseline has the error around 0.29. So the validation rates are higher than ConvNets baseline. Although the training loss can keep reducing, but it looks like overfitting. So it's important to use a good baseline to compare with your model. And you can see the simple prediction works very well for different kinds of time series data, such as stock prediction. If you just use today's stock price to predict tomorrow, you will also get a very low mean absolute error. Okay, so it's important to add the common sense baseline in your comparison. Now let's build our recurrent neural network. We choose the gated recurrent unit, which is simpler than LSTM but has similar performance. Okay, so we create a sequential model, then we add the GRU layer. One layer start GRU is our hidden layer, and we choose the same output dimension as densely connected layer, which is 32, and the one output neuron. So the results or other parameters are sent to be a good fair comparison with the densely connected network. The result is shown here. Fortunately, the RNN works better than densely connected network. Right? We can see now the validation loss is lower than 0.3, and it's better than the common sense baseline or slightly. So we can see that recurrent neural networks is suitable for time series data problem. Let's try some advanced techniques. We can stack multiple recurrent layers. Okay, remember when you want to stack multiple recurrent layers, multiple GRU, you need to set the recurrent sequence to true for the hidden layers, but not for the output layer. Okay, so we add one more GRU layer here, and we can set the dropout and the recurrent dropout for this layer. So we try some advanced techniques. Okay, so the hidden layer, second GRU layer, and the output dense layer. The result is here. Now is slightly better. Not much better than previous method. Although the training loss can keep reducing, but the validation loss didn't change a lot. Which means overfitting. So it's slightly better than single GRU. Of course, we didn't optimize the hyperparameters. We can try different dropout ratio or different recurrent dropout ratio, but it shows that how difficult to beat common sense baseline for time series data. Another technique is bidirectional RNN. A bidirectional RNN exploits the order sensitivity of RNN. Here is an example. The bidirectional means the layer will send the original chronological sequence into the RNN and also reverse the sequence and then send the reverse series into the RNN as well. So it's called bidirectional, the normal sequence and the reversed sequence, and then both will be passed to RNN model, and then the outputs will be merged by add or concatenate. This is bidirectional RNN. It's useful for natural language processing because sometimes we say a sentence in reverse order or in different orders, but it may not be work for time series data like stock price or temperature. Let's try to use reverse data to train our model and see if that reverse data can work for forecasting. And we can see that the reverse data performed much worse than all previous models, even much worse than common sense baseline. It has a very high error rate, very high loss, right? Higher than 0.4. So the reverse data do not work for temperature forecasting. But how about the bidirectional GRU? Actually, the bidirectional GRU gets similar performance with regular GRU because the model can learn use just a single branch, use the normal sequence, normal order branch to predict and ignore the reverse order. So if you try the bidirectional GRU, just add one bidirectional layer and then paste the GRU layer into the bidirectional layer, then the Keras will automatically create two branch model for you. And this model, if you train it carefully, it can intelligently learn use only one single branch, not the other reverse branch to predict. So eventually you will get similar performance with regular GRU, just with double parameter size. There are many other techniques we can try to make our model better. We can adjust the number of units in each recurrent layers in the stacked setup, or we can adjust the learning rate used by the RMS prop optimizer, or even try different optimizer. And we can try LSTM models instead of GRU model. Also, we can try a bigger density connected regressor on top of the recurrent layers. We can combine the density network, feed-through networks with the recurrent layers. Finally, don't forget to run the best performing model on the test set. Anyway, it shows us how difficult it is to beat a common sense model. So be careful when you do a time series problem. Don't forget to compare your performance with common sense baseline. We can also use convolution networks to process time series data. We can use the 1D convolution for sequence data. Previously, we used the 2D convolution for image data, or 3D because image data include colors. But for the time series data, we just need to use 1D convolution, and it looks like this. We will define window size to select a series of data, then apply convolution filter to calculate one output results. Let's build a 1D convolution model for classifying IMDB movie review. So we can import the convolution 1D layers. It's like the 2D version. We have the convolution 1D, and we can assign the filter size, and then the max pooling 1D, the convolution 1D, and the global max pooling 1D. Finally, we will add one dense layer with sigmoid activation function. Here's the accuracy, training and the validation accuracy of IMDB movie review classification. We can see that the performance is not bad. 1D convolution can generate similar accuracy as LSTM or GRU model, but is much faster in training. We can go further by combining CNN and RNN models for long sequence. Suppose we have a high resolution data, time series data. We can first apply 1D CNN to filter the data to shorten the sequence, and then process, then paste the shorter sequence to RNN for processing. This picture shows the idea. A long sequence is filtered by 1D CNN model. CNN will merge multiple data into one, and the shorter sequence can be sent to RNN, and the RNN can better be trained on the shorter sequence. So using Keras, we first add a convolution 1D layer in our sequential model, and then do max pooling convolution, and finally send the shorter sequence to the GRU, the recurrent layer, and output the prediction. To make sure our CNN RNN model has good performance, we need to prepare higher resolution data. So we can do that by just change the step previously the step is set to 6. Now we set the step to 3. Then that will generate the higher resolution data. The results of the mixed model is shown here. Actually, it has similar results as the pure RNN model, but it can handle data with higher resolution. It is useful for other dataset. Temperature forecasting is too simple and cannot show the strength of the mixed model. In 2018, some researchers were curious about the performance of generic convolutional network and tried to compare with different recurrent neural networks on a large-scale RNN benchmarks. Okay, so this paper has been published in 2018, and the title is called An Empirical Evaluation of Generic Convolutional and Recurrent Networks for Sequence Modeling. Okay, and surprisingly, they find that a simple temporal CNN model can outperform RNN and LSTM across a diverse range of text and data sets. This paper has drawn attention from Jan Lacken, and he posted a message on Facebook that said, "We knew CNN is better than RNN and LSTM for a while," and his post has drawn my attention. That's why I first noticed this paper. Because he is the inventor of CNN, so I took his comments with a grain of salt. Here is the architecture of temporal convolution network, TCN. It's actually multi-layer 1D convolution with a residual block. So the architecture looks like this: multi-layer 1D convolution with a skip connection. Multiple layer 1D convolution can consider the information from longer sequence. The authors has evaluated TCN on a large scale sequential benchmark, and he compared with LSTM, GRU, and RNN. We can see that the TCN has outperformed other models on most data sets, right? Some datasets use accuracy as metric, other datasets use loss. We can see LSTM and GRU are much better than RNN, and some datasets GRU has better performance, but the TCN can outperform them all. That shows the 1D CNN is very promising. Later, another blog caught my attention. The title is very sharp. It is The Fall of RNN and LSTM. It was published by a professor of biomedical engineering, Purdue University. The author claimed that the RNN and LSTM should be replaced by a new architecture called attention. Here shows the idea of hierarchical attention module. The attention module will give the different parts of data different scores to highlight the importance of the data. So usually we can encode the data and then pass through multiple layers of attention module. And more evidence shows that the attention module can outperform the RNN and LSTM model. One of the reasons that attention can outperform RNN and LSTM because that our brain does not cares about the order of characters very much. We first have an overview of the whole world, and then we try to examine the order of the characters. Here's an example. You can try to read this sentence. I got a big what? But however, after read it second times, you can find that the B and the D has been switched. So I got a big. And the second sentence says that you let read wrong, but actually it's again should be you read let wrong. So the final sentence said you read that wrong too. This example can show us that our brain does not read all the sequence of characters at the first glance, but we just give an overview of the words and then explain the order of characters later. In 2017, a breakthrough paper called "Attention is All You Need" has been published, and it shows that attention, especially a new model called transformer, can outperform RNN and LSTM on NLP, and the architecture has been widely applied to different areas such as speech and computer vision. Today, we will use transformer instead of RNN and LSTM. However, RNN and LSTM is still useful for some time series data problem.